When you train a model, the training loss just keeps dropping, epoch after epoch, seemingly forever. So more training is always better, right? Not even close. Watch the validation loss instead, and you'll see it fall for a while, hit a bottom, and then start creeping back up as the model begins memorizing noise. The best model isn't the one you get at the end, it's the one you had at that bottom. Early stopping is the almost embarrassingly simple idea of quitting right there, at the peak. Let's dig in. So what goes wrong if you just train all the way to the end? Here's the contrast. Train until the training loss bottoms out, and you've almost certainly gone too far. The training curve keeps improving, which feels like progress, but somewhere along the way the validation loss turned around and started rising. The model has stopped learning general patterns and begun memorizing the noise in your training data, and that is exactly overfitting. Early stopping catches the model at its peak instead. It watches a validation metric and halts training right around the point where that metric stopped improving, then hands you the best checkpoint. You get the version that generalizes best without wasting compute pushing deeper into the overfitting zone. So how does early stopping decide the exact moment to quit? Follow the loop one step at a time. Every epoch, you do the usual training, then measure performance on a held-out validation set. This is the signal that actually matters because it reflects how the model does on data it never trained on, not just how well it fits what it has already seen. Whenever that validation score improves on the best you've seen so far, you save the model right then as your best checkpoint. This running snapshot means you always have the strongest version on hand, no matter what happens in the epochs that follow. But a single bad epoch doesn't mean it's over. You wait through a set number of epochs with no improvement, a window called the patience, before you actually stop. That patience keeps a noisy blip or a temporary plateau from ending the run too early. Once the patience window passes with no new best, training halts, and you restore the weights from that best scoring checkpoint. You throw away the later, overfit epochs and keep the model exactly at its peak validation performance. Strip it down, and 3 ideas define early stopping. It halts when validation stops improving. Rather than training for a fixed number of epochs, early stopping watches a validation metric and quits once that metric has plateaued, catching the model right before it tips into overfitting. Patience keeps it from quitting too soon. Instead of stopping at the first bad epoch, it waits through a set number of non-improving epochs, so a noisy dip or a brief plateau doesn't cut a promising run short before it recovers. It's nearly free regularization. You already compute validation metrics, so it costs almost nothing, needs no change to the model or the loss, and simply restores the best checkpoint, behaving a lot like weight decay by limiting how far the weights drift. All right, let's lock in the essentials. Early stopping is the cheapest regularizer in deep learning, halting training the moment validation performance stops improving, right before the model starts to overfit. It works because validation loss follows a U-shape, falling as the model learns real patterns, then rising as it memorizes noise, and you want to stop at that bottom. Patience is the number of epochs it waits without improvement before stopping, which prevents quitting on a noisy plateau, after which it restores the best checkpoint. Just remember, it needs a proper held-out validation set, and never tune the stopping point on your test data. If deep learning explained as plainly is what you're after, plenty more is waiting for you at Standarity.com. See you inside.